Thank you. So this talk has two parts. First, I'm going to introduce Turnstile Plus, which is a new framework that we created that helps programmers implement complete typed languages, and in particular, dependently typed languages. So what sorts of specific things can you do with Turnstile Plus? Well, say you want to create a typed DSL, but you don't want to do all the work by yourself from scratch. Turnstile Plus can help you with that. Or say you're a type theorist and you have an idea for a new type theory. If you implement your idea with Turnstile Plus, you can have a concrete language with which to experiment and play with, and as a result, you can iterate on your design more quickly. In the second part of the talk, I'm going to introduce Cur, which is a new proof assistant that we created with Turnstile Plus. And the unique thing about Cur is that it's extensible. So if you want to add a new feature, or if you have an idea for improving a feature in the proof assistant, like pattern matching or termination checking, you can do so very easily. And the best part is that you can do so modularly. So this means that you can extend the language without having to touch the rest of the implementation of the compiler. And existing code doesn't have to change either. Or since proof assistants are typically not just one language, but instead a collection of interacting languages, with Cur, it's easy to add one more language, like a tactic system, to this system. And in Cur, this new language will be integrated with the rest of the system in a nice, supported way. So let's dive right in here. Here's some Turnstile Plus code. It's an implementation for a complete dependently typed core language. You don't have to read all of this code. The details are in the paper. I just want to highlight a few key things. First, Turnstile Plus programmers can implement types for their language in a very concise way. So here we have type, which is the type of types. And like any good tutorial, we give type a type that's equal to itself. And also here's pi, which is the dependent function type. And it's a little more complicated, but as you can see, it's still a very concise implementation. To implement the main part of the language, Turnstile Plus programmers write type check and elaborate rules, like you see here for lambda and function application. And they write these rules, again, with a very high-level inference rule syntax that's very similar to what you would see in a paper or a textbook. These rules are binding aware, so it's not too much extra work to implement a binding form like lambda. And the best part is that the binding support is at the level of the surface syntax. So you don't have to switch to some alternate representation of binders like the Breuil indices. Turnstile Plus also has support for type environments. You may notice that there's no gammas to the left of the turnstile here, and that's because existing environment bindings are automatically propagated according to lexical scope. And so programmers only have to write new bindings that they want to add to the environment, like you see here. And finally, for this example, programmers can implement type-level computation by writing reduction rules like beta here, that again is very similar to what you would write on paper and pencil. And Turnstile Plus then takes these equivalences and uses it during type normalization before it compares types for equality. So now that we have a complete language implementation, let's try to use it. Let's see how to use it. Before we use it, we have to do a few more steps. First, we take this code, we put it in a file or a module. It's the same thing. And here we give it a name, dep. And then at the top of the module, we have to declare what the language of the code in the module with this hashlang declaration. So here we're writing Turnstile Plus code, so we write hashlang Turnstile Plus. And now we have to make the constructs that we want in our language available by exporting them. So here we're exporting pi, type, and then type lambda and type application, except we're renaming type lambda to lambda, and we're renaming typed application to this hash %app, which is here it's a special name that means that our language will have implicit function applications. So programmers can just write f applied to x as opposed to an explicit apply f to x. And so once we do all this, we have a language. And the name of our language is exactly the same as the module, dep. So now let's see how a programmer can use it. Here's the same language in a smaller box. And to use the language, a programmer just has to create a new module and then write #lang and the name of the new language. Here it's dep. And then the code in the module will now use the implementation of our language. So that's how to use the language. But that's only one of the things you can do with languages that you create with Turnstile Plus. So what else can you do? Well, languages created with Turnstile Plus are easily extensible, and in particular, you can extend the type system. Let's look at an example of that. Here's the same dep language, and now let's say we want to add, we want to extend the language with natural numbers. All we have to do is create a new module, and in this module, we implement natural numbers in the usual way. We have a nat type and the 0 and successor constructors. And we also have a new type rule that eliminates nats and a reduction for this eliminator. And the point that I want to make is that this library is extending the type system with new rules. And with this library, if all a programmer has to do to use this extended type system is import the library the same way they would import any normal library. So that's extension. Another thing that you can do with languages created in our framework is reuse language or reuse specific constructs in the language. Let's look at an example of that. Here's the same language again. But now, let's say we want to create a new language called dep plus ind here. And in this new language, we want the programmers of this language to be able to define inductive data types. But instead of re-implementing lambda and function application, we instead import them from our old language and then reuse the implementation. So now, someone using this new dep plus ind language can use the new defined data type construct, but also the application in lambda from the previous language. So that's reuse. A third thing that you can do with languages created with Turnstile Plus is to have them interact together in a nice way. And they can do this because they share a common substrate. So what is this common substrate? It's macros. And specifically, Turnstile Plus uses Racket's macro system to implement its languages. And here's just one example of how it makes use of macros. Here's the definition of beta that we saw before. When this definition is compiled, it compiles to a plain macro definition. And well, why do this? Why would we want to do this? And that's because when we do type normalization, is essentially what we're doing is we're rewriting one piece of syntax to another piece of syntax, and that's exactly what a macro system is good at, and so it's a very natural implementation. Here, specifically, the readx becomes a pattern that's an input to the macro, and the contractum creates the result of the reduction, and that's the output to the macro. And so since we are normalizing types using macros, we call this normalization by macro expansion. So this macro needs a second case. So the first case handles the case when we have a beta readx. But what if it's not a readx? In this case, the macro produces a neutral term. But this neutral term needs to be able to communicate to later reductions that, hey, I could be a beta readx later. So you have to check to see if I can be reduced. And the macro system, again, has a nice way to do this communication, which is you can tag pieces of syntax with meta information. So here, we have a placeholder at the head of the neutral term, and it's tagged with it's tagged with meta information that says I'm a potential beta redex, and this communicates to later future reductions that they need to check this neutral term to see if it can potentially be reduced. And so in general, the system of tagging syntax with meta information is very useful, and it's used a lot in our system. For example, the type rules also communicate type information in this way. All right, so languages created with Turnstile Plus can communicate in a nice way because they're all implemented with an underlying macro system. But Turnstile Plus doesn't just use the macro system internally. It makes all of the tools available to users of Turnstile Plus as well. And so users have a nice toolbox that they can use to further build languages and systems. And some of these tools are just exactly what we've seen, which is a convenient way to transform and manipulate syntax, propagation of meta information on syntax, and also the ability to overload various features, which helps with modularity. So when might it be useful to have a framework that's good at creating collections of interacting languages? Well, a proof assistant typically consists of a core calculus implementation, but then this core has a lot of extensions to help programmers use it. For example, you might want inductive data types. You might want to let programmers write recursive functions. But then if you have recursive functions, you need a termination checker. Pattern matching is also a convenient feature that many programmers like. Also, implicit arguments are also a convenient feature, but if you have implicit arguments, you need a unification algorithm. And as I mentioned before, proof assistants typically, they're not just one language. They have helper languages, like a tactic DSL a lot of times, to help programmers write code. And a lot of times there's some sort of automation to help programmers search for proof terms. And so the point I want to make is that a proof assistant is exactly a collection of interacting DSLs and extensions and components. But this architecture makes it very hard to sort of experiment, to extend, and to iterate on the design of proof assistants. And so typically, if you want to add a feature to some proof assistant, what many people wind up doing is just forking the entire repository, and then you have to go figure out how to modify the compiler. And then if you want to add like a third-party DSL, a lot of times it's implemented separately and is only loosely coupled with the rest of the system. So with this in mind, we created a new proof assistant that we wanted to be able to more easily experiment because we're language researchers after all. So we wanted a proof assistant that is modular and extensible, and so we created one called Cur. And it has all these components, and we created it with Turnstile Plus because Turnstile Plus made it easy to implement all of these sort of interacting components. And in addition, we made use of many of the macro tools that are also included with Turnstile Plus. And in the rest of the talk, I just want to give a very, very high level, explain at a very high level how macros helped us implement many of the parts of Cur. So I already mentioned that Cur has a tactics DSL, and then we implemented a meta tactic DSL to help us write the tactics. But the point I want to make is that tactics inherently are just you're just manipulating syntax, right? You need a little bit of extra plumbing to keep track of the proof state, but at their essence, they're just syntax transformers, and so macros were a very natural fit to implement the tactic system. We also added a little bit of automation by calling out to a solver and what this library does is it provides a new construct for defining axioms, and this construct first calls out to the solver and only defines the axiom if the solver is able to verify the proposition. But here we wound up with a whole bunch of, we wanted to be able to more finely classify sort of these axioms, because in Kerr you can also define axioms the typical way that you find in other proof assistants. So we had all these different kinds of axioms, and we wanted to be able to classify them to track them. And so here, tagging them with meta information on the pieces of syntax was very useful. And finally, we we implemented an experimental size type library. For those that are not familiar, size types are an alternate way to do termination checking in the type checker. But sort of the idea that we wanted to explore is in a typical size type system, the size type checking seems to be more or less separate from the rest of the type checker, and we wanted to try to implement size types in a modular way, such that the size type checking was done by a sort of an auxiliary type system, I'm calling it here. Okay, and so we were able to do this. We implemented a size type library. It's very modular. We didn't have to touch the rest of the compiler to implement it. And this library, to implement this library, we used various overloading, like type equality and function definition. So to summarize, I presented two systems. Turnstile Plus, which is a new framework that helps programmers implement extensible, reusable, and interacting dependently typed languages. And also Kerr, which is a new proof assistant that is extensible that we created with Turnstile Plus and macros. Thank you very much.
Thank you. Other questions?
Hi, this is really interesting. I have a question about Turnstile Plus. Way back towards the beginning, you introduced some example syntax from the language, pointed out there aren't any gammas because something about scoping implies that it'll just be passed along. Let's say I'm implementing a substructural type system and I don't always want to pass along iota hat in the context. How do I do this in Turnstile Plus?
Yeah, so you can definitely do it. You may have to, right, what I explained is just sort of the default. You can always choose to sort of manage the environments a little bit more on your own. And this is definitely, we have many examples where we've done this. Yeah, I just didn't show it, but it's definitely doable. Yeah.
Cool. Right, so here I have a Slido question, which is how do you handle fundamental parts of the type system like universes? Can the language designer change that, and what are the limits of extensibility?
Yeah, that's a good question. Kerr actually implements a universe hierarchy, so it's definitely doable. The support from Turnstile Plus abstractions for that is a little more experimental because checking the universes has to be a little bit lazier than the normalization algorithm that we currently have. Yeah, we can definitely handle that.
That's a real question.
Yes. Thanks. That's really tremendously useful. Could you comment a bit on some pragmatic aspects of using this? In particular, I wonder what if I'm having errors in my language definition, which I'm sure I would have at first. How easy would it be to debug my language?
Automatically determining some kind of meta properties of.
I don't know. So can I debug the macros, or will I be exposed to all the details? One of the nice
things about the macro system is that there's built-in a nice error reporting. I didn't explain in the talk, but there's a pattern sublanguage that you write with, and built into this pattern sublanguage it tries to produce nicer error messages at the level of the surface syntax, so that you can have better abstractions. The terms that you define in Turnstile Plus are true abstractions, and it tries not to report, reveal implementation details.
So another Slido question was on strong normalization. Do you just assume that, or do you help in proving that for the system?
So that would be something nice to have, but right now, any meta properties of the language you're implementing is up to the implementer. Yeah.
The other question that was also there was, how about the efficiency of the type checkers that you are generating?
Yeah. So the efficiency largely hinges on the performance of the macro expander under the hood, and it's I would say it's pretty good. We used our Cur proof assistant to basically work through software foundations, volume 1, more or less, and so it was capable of handling that. But that being said, performance was not we didn't focus on it at all, and so there's definitely some low-hanging fruit improvements that could be made.
So if there's no other, all right. David.
I'm curious about the safety of the implementation itself. So I didn't quite understand. Is everything treated as strings in the rewriting, or is there some internal type system?
It's syntax objects, which is sort of the AST that is used internally by the macro system. So you can think of syntax objects as symbolic S expressions with a bunch of meta information attached, like the binding structure of the program. And then we add extra information like types and other information.
So sort of no guarantees arising from if I wanted to implement a type-safe kernel, for example.
No. It's inherently untyped, but there's no reason that you couldn't use a language that you create and build up that way.
Thanks.
So is there any restriction on the conversion relation? So in the example you had beta reduction. So you could imagine you want data conversion or something like that?
So conversion. It doesn't support. Well, okay, I should say the what you saw. It doesn't take into account type information, but you can overload the definition, the behavior of type equality in general. And so you would be able to implement what you suggest that way. Yeah.
Okay. All right, that seems to it. Thank you for the presentation. And